So to wrap up 30, 60, 90 triangles, we're going to make an argument and actually derive the relationship that we have here. Now, it's key to understand how a 30, 60, 90 triangle is produced. So let's take a look at a specific type of triangle that we have here. So we have an equilateral triangle right here because all of the angles are congruent, and that means all of the side lengths are congruent as well. Now, it's important to notice that the angles are all 60 degrees in an equilateral or equiangular triangle. So what I want you to imagine is that we take this triangle and we cut it in half. But before we do that, we're going to label this so that we get the same labeling system that we have over here on the left. So I'm going to call each side of this triangle 2x. So this is 2x, this is going to be 2x, this is going to be 2x. I could have used any variable. They just all have to be the same. So we're going to go ahead, and I want you to imagine cutting this triangle right down the middle. So if we cut this in half, the line that we cut it in half is going to be perpendicular to the bottom of the triangle, and it's also going to split the angle at the top in half. And let's think about the triangle that we're left with. So we're left with a triangle where this is 60 degrees, because this is a 60-degree angle. The angle at the top gets cut in half, so this is 30 degrees. And then we have our 90-degree angle at the bottom here. So we are left with a 30, 60, 90 triangle. So it's important to understand that a 30, 60, 90 triangle is produced from cutting an equilateral triangle in half. Now this side hasn't changed. This is 2x. Right? Now, because we've cut the bottom in half, and this was originally 2x here, that means that this side is just x. So we have our 2x and we have our x that matches our relationship over here, but we still do not have a formula for the long leg in terms of x. So let's go ahead and label the sides that we have right now. So we know that this is the hypotenuse. We know that this is the short leg. So to come up with an equation for the long leg in terms of x, we're going to look to the Pythagorean theorem, just like we did with the 45, 45, 90 triangle. So we're going to call this side A, we're going to call this side B, and then our hypotenuse will be C. So if we start off with the Pythagorean theorem, we get A squared plus B squared equals C squared. A squared, we don't have anything for, so we're going to leave that as A squared. B squared is x squared, and C squared is going to be 2x squared. So let's go ahead and simplify this, see if we can come up with something for A squared. So we get A squared plus x squared. 2x squared is 4x squared, because it's 2x times 2x. So I'm trying to get A by itself, so I'm going to subtract x squared from both sides. 4x squared minus x squared gives us 3x squared. And then in order to get A by itself, we're going to take the square root of both sides. So the square root of A squared is A. The square root of 3x squared, we're going to use the fact that radicals distribute over multiplication, just like we did with the 45, 45, 90 triangle. And we get the square root of 3 times the square root of x squared. And lastly, the square root of 3 times the square root of x squared. The square root of x squared becomes x. So we get the square root of 3 times x. So this is our remaining side, or the long leg, which matches the relationship that we have over here. It's probably easier to remember this idea rather than remembering the whole process to derive it, but I think it's important to see where it comes from.